Hi, my name is Euiwoong, and then I want to talk about separating Grothendieck problem from Little-Grothendieck, or with respect to NP-Hardness. So this is a joint work with Vijay Bhattiprolu from IES and then Madhur Tulsiani from TTIC. And then our problem is like this, like fundamental Grothendieck problem. So the input is a m by n matrix A, and then our job is to find two vectors, m-dimensional x and then n-dimensional y. Both are like plus minus one vectors to maximize the quadratic form or like bilinear form x transpose A1. Okay, so this is a fundamental problem. Yeah, and then unlike some problems like the value of some solutions may be negative. Yeah, but then one can easily say that for any matrix A, the optimal value is non-negative, so that the approximation ratio is well defined. And then of course, like this problem is started by this like fundamental work of Grothendieck that essentially shows that there exists order 1 approximation algorithm for this problem via STP rounding. So since then, yeah, this problem has like various applications to many fields, including function analysis, combinatorics, and optimization. And then today we're going to study the question: what is the best approximation ratio achieved by any polynomial algorithm? Okay, but then like before diving into the problem, let's try to see like some related problems, generalization or special case, and see how our problem is different from those results. And then the first problem we're going to see is slightly more general problem called the quadratic maximization. Okay, so here the input is like the n by n matrix A. One can even assume that A is a symmetric. And then we want to find just like one vector, x, to maximize x transpose AX. Of course, one can easily say this is a generalization of our problem. But then here, like you gotta be careful because, like for example, if A is a negative definite, then the optimum itself can be negative. So in order to use approximation, then like some assumptions are needed. And then yeah, one natural way to do is to at least assume that diagonals like vanish. So if you assume that AII is a 0 for every I, then there exists an order log n approximation algorithm, independently discovered by many groups. And then this is essentially tight. And Arrow et al. Prove the almost matching hardness. Okay, so log n is good. And then the second problem we're going to see, which is more relevant for this talk, is a special case called the PSD quadratic maximization, or like Little-Grothendieck problem. Okay, so here everything's the same as before, but then like matrix A is a promise to be like PSD matrix. For example, A can be decomposed as like B transpose B for some other matrix B. Okay, so this is this is a problem. But then yeah, one may wonder still like yeah, we are trying to find one vector. Okay, so how is that related to like our problem, which is like bilinear problem, where like we are trying to find two vectors? Actually, one can see that if A is promised to be PSD, then finding one vector and then finding two vectors are actually like the same thing. Okay, so formally one can see that the maximum value of x transpose AY, where we search over like two vectors x and y, because like A has admits this decomposition. One can say that, okay, so then it's equal to the maximizing inner product between bx and by like this. But then we are like, yeah, the bx and by are in the same search space. So it's nothing but searching like just like the one thing, bx, and then try to maximize its L2 square. Then it's nothing but maximizing over like just one vector x. Okay, so yeah, in this case, then yeah, one can see that if like A is a PSD, then like one vector and two vector are the same thing. And that's why this problem is a special case of our Grothendieck problem, where we are like searching over two vectors for general matrix. And then for this problem, like the pi-over-2 approximation exists. So that's discovered by Nesterov. And then Bhattiprolu show that this actually is tight. It's NP-hard to do better than pi-over-2 by like any small constant. Okay, so those are like these like two special case and general case. But then our problem, Grothendieck problem, has like a slightly more interesting history. Okay, so this is our problem. And then from the upper bound side, okay, so we already said that Grothendieck gave a constant vector approximation algorithm. And then for a long time, the best approximation ratio was this number achieved by Cravin, which is like roughly 1.78. And then in 2013, Braverman et al. Showed that this number is not tight. And then actually it can be one can get slightly better approximation ratio. And then all these upper bounds are achieved by STP rounding, in a sense that all these like numbers also give us the STP gaps, upper bounds for STP gaps. Okay, so yeah, we often call like KG as like the worst integrality gap constant. And then until now, like the exact value of KG is not known. But then yeah, we know that it's slightly less than 1.78. Okay, from the lower bound side, if you look at KG, then Davy and Riz independently give a lower bound of KG, which is like the integrality gap for STP, which is a 1.6769, which is like slightly lower than the best upper bound. So one can say there's some gap. And then if you look at the computational hardness, then Cote and O'Donnell prove that assuming the unique games conjecture, so one can translate Davy-Lee's like lower STP lower bound to computational hardness. Okay, so that they prove that it's NP-hard to approximate this problem better than Davy-Lee's constant, assuming unique games conjecture. And then shortly after, Raghavendra and Stoiter show that we don't know what KG is, but then whatever KG is, actually it's going to be NP-hard to do better than KG, assuming unique games conjecture. Okay, so that's the best known for unique games. And then in some sense, like if you assume unique games, then actually the problem is like solved. We understand the approximation ratio exactly. But then still, if you only want to base your like result on P is not equal to NP, then the best hardness is a pi over 2 from Little-Grothendieck proved by Briet, Regev, Saket. So there's like some gap between what we can prove using NP hardness and then what you can prove using unique games conjecture. Okay, so there's like some gap between these two, or even these two. And then yeah, if like unique games conjecture is false, then it may be possible that the approximation ratio for Grothendieck problem is equal to the approximation ratio for the Little-Grothendieck. Okay, so if like unique games is false. Okay, so that was a situation, but then our result shows that actually it's not going to be true. Okay, so we show that it's NP-hard to approximate even the original Grothendieck problem within a factor pi over 2 plus epsilon for like some small but universal constant epsilon. Okay, so the bound we got is only like 10 to the minus 6, but then it's unoptimized, plus one can be bigger. So conceptually, we kind of separated the Grothendieck and then Little-Grothendieck, only assuming the P is not equal to NP. And then yeah, we're gonna mention technique more in detail, but then it's more like global analysis compared to more like local analysis that we typically use for unique games hardness for the other NP hardness. So it may be useful for like the problem itself or like many other problems. Okay, so that's our like main result. And then yeah, let me talk about proof a bit. But then like before like directly jumping into NP hardness, let's revisit how the UG hardness is proved. And then get some inspirations from it. Okay, so of course, like yeah, if you want to prove unique games hardness, then the first thing you gotta do is construct a dictatorship test. So in our context, so dictatorship test is just nothing but some like instance, which is nothing but a matrix A. But then we're gonna assume that A has like this special structure. Okay, so we're gonna assume that A is like 2 to the R by 2 to the R matrix. So that the decision variables, F and G's are like 2 to the R dimensional functions. 2 to the R dimensional vectors. Then yeah, one can treat like F and G as a Boolean function. Okay, mapping R dimensional vector plus minus 1 to the R to plus minus 1. Then like that brings us to like a very like standard Boolean function analysis setting. And then of course, then what we want to show that if like F and G are dictators, matching dictators. For example, F and G are both dictated by the ith coordinate. Then yeah, we want say that the value of this solution is pretty good, say 1. And then if the F and G are like far from dictators, then we want to say that the value is small. Okay, so this is a typical requirement for dictatorship function. And then of course, like since we are looking at the F and G as a Boolean functions, then yeah, one can bring all this like standard notions from the Boolean analysis literature. So for example, yeah, for given any function f, one can look at the Fourier decomposition summation over all subsets S, the Fourier coefficient of S times the character of S. And then, yeah, I'm gonna define this like the standard inner product. So F inner product G is an expected value of Fx times Gx. And then we can define also P norm of F in the standard way. Okay, so this is our standard notations. Given this, okay, so then yeah, what's our like first candidate for dictatorship test? Okay, so first one is like very simple. It's just like the degree 1 projection. Okay, so our matrix is F1, which can be considered as an operator. So given a vector F, which is like Boolean function, then what F1 does is to leave only like linear part of F. Okay, so notice that yeah, we are only summing over like the size 1 linear Fourier coefficients. Okay, so as opposed to all Fourier coefficient. Okay, so this is a projection because we are only like leaving linear part of F. And then this is actually a dictatorship test. Okay, let's briefly see why you should like give something. So of course, if F and G are dictator, then one can easily say then F1 doesn't do anything because like dictators are like linear functions. Okay, so then yeah, G transpose F1, well, F is exactly 1. But then if F is far from dictator, suppose that each linear coefficient is like very small, say sub-constant, then at least one, if you look at the value of G transpose AF, since G is a plus minus 1 function, then the first thing we know, that holds for every G and F, plus minus 1, is that the value of G transpose AF is at most the L1 norm of F1F. See, so yeah, that's just like because like G is a plus minus 1 function. If a G is exactly the sign of F1F, then actually we're going to get exactly 1 norm of F1F. But then yeah, then there's like the well-known pi over 2 theorem, saying that if F is far from dictator, then the 1 norm over F1F is at most pi over 2. Okay, so it's going to be like, it depends on how far F is from dictators. So perhaps you should have a little of 1, but then let us ignore this. But then how is such a thing proved? Okay, so the core intuition is that if F is far from dictators, and then if you look at the linear part of X, linear part of F as a random variable, because X is a random, then value of this random variable is distributed like Gaussian with some variance. Okay, so this variance is formally known as level 1 weight of F, which is defined like this. Yeah, and then using this intuition,